In the last class, we started the length, how to find the length of a curve. So today we're going to learn how to find the surface area of some surface of a revolution. Okay, just means you rotate the curve around an axis. Okay, so it's a special surface that we cannot do, and we cannot find the surface area, an arbitrary surface, which belongs to Math 1462 class. Okay, it's called differential geometry. Okay, if the major is flow mechanics, for example, more advanced mathematics course should be taken, like especially in geometry. Guys, because when you try to understand the flow, airflow, like pass by the surface, the shape of the surface, it's very important how to describe it and how to find equations to describe the flow. It's very very challenging problem, and still going on researching. Okay. So my opinion is, if you want to become expert in flow mechanics, you have to have a master's degree in geometry, in mathematics first. Okay, otherwise there will be a problem. It's hard to use mathematics to solve those complicated problems in flow mechanics. All right, so we are going to talk about a special surface area. But the first one we know that if you have a cylinder, cylinder is a very special surface. How to find the area of the cylinder without top and bottom, okay? And we know that if this is a length, if this is radius, right? How do you do that? You open the cylinder, you cut the cylinder from bottom to the top, and you open it, and this becomes a rectangle. So it's easy to understand that formula. It's 2 pi r and L after you cut it, open it, right? So the area, the surface area, you can figure it out. It's 2 pi r times L. 2 pi r is the length of the rectangle, okay, which is the circumference of the circle. Now, the difficult part is how to find the surface area of this portion. This portion, okay, it's not without the top of the cone. So this is L, okay, but you have two radius, R1 and R2. I'm not going to derive the formula for you here. It takes too much time, but you should see the formula. If you cut the cone, open it, how does it look like? I think it looks like that. It's a sector. Okay, if we open it, maybe it goes like that. Right? Yeah. Okay, so this is a part. Okay, how do you find the area of sector? Depends on the angle here. Okay, it depends on the angle. Okay, so you take the difference. Okay, the angle. Yeah, remember the formula we have for the sector, right? If we have an angle, this is sector, and this is a capital R, and the area of this is going to be half pi theta r squared, when then divided by 2. When theta is 2 pi, you get to complete the disk with radius r. 2 pi divided by 2, just pi. Okay, you can use this formula to find the area of this portion. Now let me call it. Yeah, this is a portion we're talking about, right? After you open it, and you get this piece. All you have to do is just to take the difference, the larger set minus the smaller set, and this is the L, okay? And then Yeah, the circumference here is 2 pi r1. That's a 2 pi r2, right? The length, right? The arc length corresponding to the angle, okay? And well, anyway, so this is the area, the surface area. I give you the formula. Maybe you can try to figure it out, okay? It's going to be still 2 pi, but it's 2 pi L. So what is R? R is the average value of this two, okay? L is the same L, okay? Slightly different from the above, but it's reasonable, right? All right, yeah. So if you have a time, don't look at the book. Just try to derive it by yourself. All you need is a knowledge is very simple algebra from middle school. Okay, that doesn't require very advanced mathematics. But I already showed the picture. You cut the cone, open it, and you have to figure out the theta. Okay, and express the theta in terms of other quantities. In terms of quantities, then you take the difference of the areas of the two sectors. Then you get the area of the remaining, and then you end up with that formula. Okay. Okay. So you probably have to introduce capital R. I know this one, capital R, and this is R2. So L is giving me the difference of those two. Okay. Yeah. So I'm not going to spend too much time on that. We use that. Right. So the reason we want to use that is suppose we have an axis. Okay, this is an axis. Okay, and you have a curve here. Okay, you want to rotate this curve around this axis to generate a surface. Okay, generate a surface. Okay, so this is the surface you get. So the question is, how do we find the area? So first of all, you know how to find the length of the curve, right? The length of the curve. So this is yeah. So the idea is that you chop, yeah, you cut, yeah, you cut the cylinder. This is generalized cylinder, okay? You cut the surface into slices. Okay, into slice. So you want to find the area of that slice and add it together. So how do you do that? Along the curve, the change is the arc length. This is the S. This is S plus ds. Okay. Okay. So S is from the starting point from here. So this piece, this piece can be approximated by, yeah, this pieces can be approximated by this cone type of cylinder. Okay. And this side is a S, okay, not ds. Okay. So that piece, we know the formula, okay? The average radius is going to be this R in the middle, same point, right? So the area of this piece, I'm going to denote it by the area. I'm going to denote by dA. Okay, that just means small area. So this is a 2 pi r ds. Okay, 2 pi r ds. R is the radius, the average value of the two radius. That's almost, yeah. It's in the middle here, right? Okay, and this is R. So thinking about the surface, total surface area. Okay, is going to be add all together. All together is going to be from 2 pi r ds, and S is from 0 to L. L is the length of this curve we are going to use. Okay, this is my original formula. That's it. This is our formula. Without a 2 pi r, you get the total length of the curve, right? But put 2 pi r there, you get the surface area, okay, of this surface of revolution. Right now, then you can derive a more specific formula using this. Okay, how do you do that? There are many ways to do this. Okay, the special case 1. Okay, and the curve is given by this function. Okay, and the rotation is about the x-axis. About the x-axis. Okay, so let's draw the picture. You have to learn how to draw the 3D dimension picture. Okay, this is a curve. Its axis, y-axis. Y equals f of x. Okay. So right now you are in a 2-dimensional space. Okay, but you stay. You live in a 3-dimensional space, so it's not like out of your imagination. You live in 3-dimensional space. We draw the curve in 2-dimensional space, x, y plane. Now you're going to rotate this curve in 3-dimensional space. You create a surface. Okay. So how can I do that? Right? It's very simple. The area is going to be integral from L to L, 2 pi r ds. Okay. But I know I can change. This is the s, right? What is s? S is from here to here. What is r? R is from here, right? Okay, and this is a point on the curve as coordinates x and y. So x and y are related variables, okay, because this is a point on the curve. Now, I want to see this arc length s depends on x. It also depends on y, okay? So if y depends on x, then it depends on x. If x depends on y, then you can think s depends on y. Okay. But anyway, ds. If you want to use x, that will be 1 plus dy dx square and dx. Okay. So that means you view s as a function of x. Okay. So s is a function of x here. Okay, so ds, you can talk about derivative s with respect to x. Okay. So what is r? R is at that point, r is just y. So y coordinate of that point. But y coordinate of that point is also equal to f of x, right? Right? Yeah. So now the surface area is going to be, you change the variable from s to x. So x is from a to b, right? If a is a to b. And the 2 pi r also depends on x. So it's f of x. Then you have, and here f prime x square and the dx. That's how you get the formula. You have to understand the formula, okay? It's very important because if you don't understand the meaning of each part, you are not going to write the correct formula for the problem, okay? If you just memorize this, like 2 pi f and square 1 plus f prime x square, without understanding what is f prime x at, then if I change the problem a little bit, you will make mistakes. Okay. For example, if the axis is, if it's not, the rotation is not about the x-axis, rotation about another horizontal line. Think about that, right? If it's the same problem, you know, if y equals f of x, but the rotation is about y equals k. Okay. We assume that this is greater than equal to k. Okay. Otherwise, I cannot make a rotation. Okay, so modify this a little bit again. This is a y equals k, and this is the curve y equals f of x. So the curve is above the horizontal line. Now this time, when you rotate it, it goes like that. Okay. If you understand the original formula, then you have no trouble to solve the problem. Okay. How do you do that? You still pick up an arbitrary point x and y, right? Right? But you have to draw the radius. The radius is from here to here. This is the r, right? Right? And then s is from, this is a point. S is from arc length is from here to here. That's s, right? So the area is going to be 2 pi r ds. Okay, you can say s is from 0 to l. So you change s to the s depends on x and y, but y depends on x. So s is a function of x, but it's complicated. But what we know is ds is going to be 1 plus dy over dx. Right? I don't have a specific formula for the s, but you can find out the s. S is a function of x. How do you do that? Well, you can, if this is a, this is a b. S is going to be the integral from a to b ds, right? Which is integral 1 plus f prime x squared dx, and from a to x. Sorry. So that's why it's a function of x. Okay? Yeah. But I don't need that part. It's harder to evaluate. Okay? But I know ds is going to be this part. Right? But what is r? R is y. R is not y. R is actually y minus k this time. Okay? So you have to pay attention what is the notation here, right? Then this will be f of x minus k. So now the area is going to be from a to b, 2 pi f of x minus k, and square root of 1 minus f prime x squared dx. So you have to draw the picture. You cannot just blind when you do the problem. Hey, here's the formula, use the formula. Hey, here's the function. I put the function into the formula. Right? You have to draw the picture. So whenever do the homework, draw the picture first. This is required. It's not like I'm going to find the answer. Okay, I got the answer, I'm satisfied. Okay, you have to learn draw the graph. It's required. And when we grade the test problems, I want first thing I pay attention to what is graph. When I see the graph is wrong, I don't think you get the right answer generally. Okay, so you have to learn how to draw the graph. All right, now I'm not sure you have taken 171 already. 171, this course is about graphing. Yeah, that's a 3D graph. Okay, it's called multi-dimensional mathematics. Okay. All right, so let's take a look at, that's the first case, right? The notation is about the horizontal line, which could be the x-axis in general, okay? In most of cases, but it could be also another horizontal line. So you have to write down this original formula we call root formula. Then you have to figure out what is r, what is s. You have to mark it clearly on the picture, okay? If I don't see the picture like that, immediately I can tell this student does not understand the problem completely, not 100%. Okay, immediately I get this image, impression, impression. Okay. Then usually 50-50 chance. This is the formula is wrong because you don't understand the meaning of the formula, each term in the meaning in the formula. So it's harder to apply the right formula to the right problem. Okay. All right, so let's do let's look at the problem first, then I can look at another case. Okay, so find the surface area of the sphere with radius r, right? So we are very curious, even we first thing we have to do is a sphere. The round sphere is a special surface of revolution. Okay, so if you put it, how do you get a sphere? You use a semicircle. You rotate the semicircle around the axis, you get a sphere. This is how to get it, right? You see, you have to draw the 3D picture. Yeah, trying to find a way to draw the. It's a 3-dimensional space in 3-dimensional space. So then the semicircle is going to be given by this, right? X is greater less than, okay? All right. So this is a notation about x-axis. So the radius, this is an arbitrary point x and y on the semicircle. So y depends on x. So this is radius r. So the surface area is going to be integral, right? And you need a, yeah, it's a, we don't know, it's 2 pi r ds first. You write down that, okay? S is from 0 to, actually the length is pi on the top, okay? You use arc length. Up semicircle, the length is pi, okay? Then you change it to the parameter, x. You can change it to the y variable maybe, but let's change it to x. So it's 2 pi r here. R is going to be y, right? ds is going to be square root 1 plus dy dx square dx. Okay. So, but I need a function, right? So this is going to be y. You have to express y in terms of x. So that's why y is going to be r squared minus x squared. Okay. And the 1 plus, so derivative of y with respect to x. Let me show you the derivative. It's going to be negative x r squared minus x squared, because that's a derivative. Okay. And the x is from negative r to the positive r. Okay. So we find the derivative. I just put the derivative there. The derivative y with respect to x is going to be this. Okay. So let me put it. Yeah. So derivative is going to be negative x. Okay. You can keep it. All right. So let's simplify it. How do you simplify it? You move this square of x r squared minus x squared into the another, yeah, combine those two. So you get r squared minus x squared, right? Plus r squared minus and actually just negative x squared. Simple. Cancel the denominator. All right, x squared canceled out. Surprise to me. It's just equal to square root r squared. And this is a constant. Okay. It's going to be 2 pi r. And then multiply by 2r. So what you get is 4 pi r squared. That is the surface area of the sphere. Good. So we were wondering, what is a surface area of sphere? How do we find it? Use the advanced mathematics. That's a piece of cake. But if you ask the middle school students, they say, "Oh, I know the formula." Just cannot tell how to do that, right? This is how do we find out. This is the power of a calculus. Okay. The surface area is there. You cannot modify it. Okay. But how do you express it? Okay. That depends on human beings' ability. Okay. We create some tools to describe it, to figure out how to do it. Okay. So let's look at the case 2. The case 2 is that we rotate, the axis is a vertical. Okay. The axis is a vertical, then the function usually is given by like the x equals g of y. Y is between C and D, okay? So C and D. So this could be the curve like that, okay? Now the question is, what is axis? Is a y-axis is axis or some other vertical lines? It could be, right? So I can look at the general case, right? I'm not going to repeat again. So this is x equals k. So I assume that the curve is on the right-hand side of the curve. So that means I want to assume that it's greater than equal to k, just for example, right? So that means for any given y, right? For any given y, the x value, okay, is greater than k. So the graph is on the right side of the vertical line. So now the rotation is about x equals k. So what do you get? You get something like that. Okay, so this is a surface around this vertical line. So let's set up the integral for this. Okay, so this is the radius is going to be here. R is here. So the formula, the universal formula is going to be 2 pi r ds. This is always true. The question is how do you express r? How do you express ds? All right. So what is r? If you look at the picture, r is going to be the difference of the two coordinates. This is x and this is a k. So x minus k. Clear, right? So you have to draw the picture. Okay, you have to draw the picture. Then ds, because x is given, x is function y, it's better to differentiate x with respect to y. Then you have to take the dy out. Okay, because you are given that function x equal to g of y. X depends on y, x is a function y, so why not let ds express in terms of dy? All right, if that is the case, I needed to also replace x by g of y. Okay, now everything's fine now here, and the y is between c and d. So the surface area is going to be from c to d, 2 pi. Okay, I is a g of y minus k, and this is a dx of dy squared plus 1 dy. Right? That's it. Right, so let's take a look at the problem. Okay. We are given the following curve, x equals natural log of 2y plus 1, y is between 0 and 1. We want to set up an integral for the area. Okay, the surface is generated by rotating the curve about the axis, about the y-axis respectively. Okay, great. So first of all, yeah, rotation is about the x-axis. Second, the rotation is about the y-axis. Maybe the third one. I'm going to say the another one. Okay. Maybe the third one is the rotation is about the line y equals what? Okay. So the three problems, we are able to do all of them. Then you find, no, we don't, yeah, you have to draw the picture. Okay. If it's rotation above the axis, you don't rotate about y-axis. Read the question carefully. Okay. And so first of all, you draw the graph, two-dimensional graph. That's the first problem. Okay. We only have one formula, which is 2 pi r ds. Okay. It's nothing to the x, nothing to the y right now. But you cannot use that to evaluate because it's harder to find L, capital L is the length of the curve. It's harder to find the dependence of R on S. Okay, so we don't use that form, but we transfer this format to another, convert to this form to another way, and depends on which variable we're going to use. Notation about the x-axis. Okay, so what is curve? When y equals 0, natural log of, yeah, look at that. When y equals 0, x is going to be natural log of 1, which is 0, right? When y equals 1, x is going to be natural log of 3. Natural log of 3 is positive. So this is a 0, 0, right? When x equals natural log of 3, y equals 1. So let's draw this graph. Right. Doesn't matter how to draw it, just a curve, piece of curve. It's increasing. Clearly, it's increasing. Okay. All right. So step 1, when it's if I say notations about axis, right? This is a notation about the axis. You have to draw the graph about axis. Don't draw a graph rotate about y-axis. So it's going to be like that, right? Okay. Then you decide which variable you're going to use. Okay, there's two choices there. For the integral, it looks like you have to use x-axis, right? So take an arbitrary point x and y. Okay, the radius is this radius, clear, right? So for this picture, from the picture you can tell I equals x. Okay, you have to decide which variable you're going to use for the integral. Okay, you have two options for this particular problem. You can use x, you can use y, it doesn't matter. If you use a, but I prefer to use a y variable. Why? Because x is given already equal to y, right? So I use a y variable. Then if I use a y variable, and then x, no, this is a y variable. Okay, so it's a y variable. Yeah, look at the coordinate at I equals y. Okay, so the area, the integral y variable, y is from 0 to 1, right? Y equals 0 from 2 1, 2 pi, right? R is y. It's y, so don't need to make any changes. It's not like an f of something. See? It's 1 plus dx dy squared dy. Okay, this is a ds. This is r, right? So only you understand the problem, you can put correct. Some students put a function and then totally wrong because you don't understand what is that, right? The common mistakes is some student will put natural log of 2y plus 1 there. Then it's wrong because you don't understand what is that part. Okay, so you have to find out, you have to clearly tell me what is x or what is the radius. The radius is a y. Okay, and this is a good example for review when you for the test. Okay, then you differentiate the derivative of x with respect to y is 2y plus 1 over 2. Okay, you don't need to evaluate it. I just want to set up with you. Now, some students say, can I use the x variable? It's possible. You can use the x variable. If you want to use the x variable, it's fine. Then if you use the x variable, you have to figure out you have to figure out 2 pi r, right? Right? You have to use the x variable, right? So what is r? What is yeah? We still go back to this, right? If you use the x variable, you need to express r in terms of y in terms I in terms of x. Okay. So if we use the x variable, I is going to be y. How do you solve for y? Because x equals natural log of 2y plus 1. So 2y plus 1 equals e to the x. So y equals e to the x minus 1 divided by 2. So that is that is the dependency of the radius on x value. Okay. Then you will get, okay. Then you have 1 plus dy over dx, right? Dy over dx, and then dx, right? So when you differentiate that part, and that is going to be e to the x over 2 squared in dx. Okay. So this is another integral, but I have to determine the domain for the x variable. I already did that, right? The domain for the x variable on the top. So when y equals 0, x equals 0. When y equals 1, x equals -3. Okay. So there are 2 different integrals for the same area, for the same surface, for the area of the same surface. It's not unique, the expression. But I needed to see this part. You have to tell me what is R, what is a ds for the integral. So don't just put the formula there. Then how can I give you partial credits? I find out the formula is wrong. At least some part is wrong, right? Then it's very hard for me to get partial credits. I have a right to take all the points off because part of the formula is wrong. Okay, and you don't give me the reasons how to figure out this formula. Okay, if you make a machine, then some part is wrong. The machine doesn't work at all. It's still useless work. Okay, but if you show me how do you make it, maybe okay, you do have some knowledge about that, so we still you deserve some credits. You just give me the product, here's the product, and then it's not working, right? So then it's harder for me to give you credits. Okay, so if you draw the picture, you draw the R and mark the R and tell me which variable you're going to use, and maybe there's a small computation mistake there. You know, that's fine. You know, it looks like you understand the problem. Okay, so let's take a look at the second part. The rotation is about the y-axis. Yeah, the most problem is you find the surface area for totally wrong picture. But the idea for that picture is correct. But I'm asking you to find the surface area for the surface around the y-axis, but you work on another surface around the axis. It's very hard for me to give you credits even, right? Because you are working on completely change the problem. Okay, so you have to draw the picture. Okay, you have to learn how to draw the picture. So this is a curve. Okay, if you rotate this curve around the y-axis, it should be like that, right? So it's a complete different surface. Okay, it's a complete different surface. Y is from 0 to 1. This time it's like a ball. Okay. All right, now what are we gonna do? You take a point on the curve, original curve, okay, and you draw the radius R, okay. S is from here to here, S, okay, but we don't need to know that. All we need to know is ds, but you have to decide which variable you're going to use, okay. And you look at, yeah, so you have 2 options. You have this, you have dy over dx squared dx. You also have dx dy squared plus 1 dy. You have to make a right choice. Okay, it depends on what you given, because if you're given x equals, sometimes you cannot solve for that. So if you are given, you know, x equals natural log of 2y plus 1, it's better to use y variable. Then you don't need to solve for y in terms of x, right? Now, sometimes you even cannot solve for y in terms of x. So it's better just to use a y variable. So the second part should be more natural. Right? Then R is going to be what? R is going to be x. right? I is going to be the x coordinate. Clear, right? It's not y this time. But you have to express r in terms of y. So it's natural log of 2y. Everything's fine now. Okay, so the surface area is going to be integral y is from 0 to 1, 2 pi. I is going to be natural log of 2y plus 1. And this will be the derivative. It's going to be 2y plus 1, 2 square plus 1 dy. All right. Yeah. But if you really want to find using x variable, it's possible. I said that. If you want to use the x variable, then you have to solve for y. The reason is you have to use a dy dx, right? So if we want to, if we want to use the x variable, what are you going to do? If you use the x variable, then you solve for, then you solve for y. It's going to be e to the x minus 1 divided by 2. And here y is between 0 and 1. Then x is between 0 and the natural log of 3, okay? All right. So then the area is going to be integral from 0 to natural log of 3, 2 pi r. I is x. I don't need to make any change. I equals x, remember. Okay? And then the derivative y with respect to x is just e to the x divided by 2. It's not too bad, right? This is another integral for the surface area, okay, of that. So, which is similar to the above one, but let's compare what do we get? See, look at this. This part is different, right? See, compare with this one. Here's the x. Okay. We are talking about different surface right now. One is the surface around the y-axis, other one is surface around the x-axis. Okay. Another problem is here is third one is the rotation is about the line y equals 1. So let's draw the picture. Okay, this is going to be natural log of 3 and 1, right? Okay, this is a line. Okay, let's draw the surface. It's rotated around the line y equals 1. It goes like that. Right? All right, so take arbitrary point, x and y, and you needed to draw the radius. Okay, so from here to here, it's s, that's r. Okay, my original formula is going to be 2 pi r ds. This is a universal formula. Okay, it's always true, right? The question is, you have to decide which variable we're going to use. In this particular problem, you can use x, you can use y, doesn't matter. Second, right? And then if you use x, you change everything to the x. If you use a y variable, you change everything to the y variable. Okay? Then you get the integral of some function of y, if you use y variable. All right, so if you look at the picture, what is r? The picture shows you r is the difference 1 minus y. Clear, right? Yeah, 1 minus 1. Okay. So I prefer to use the y variable. Then in this case, the integral y is from 0 to 1, 2 pi, 1 minus y, square 1 plus the graph. You can then guarantee you always get right integral. Otherwise, you only have a 50-50 chance to get right integral. Okay, without understanding the formula in the book, you cannot, yeah, you are not able to get right integral. There are some set, yeah. So the original formula is just 2 pi RDS. Okay, and you can also use the x variable for this problem. Okay. So for some problems like that, you can use multiple. You can use 2 different integrals for the same surface area. Right? But there are some problems you cannot change this variable. It's harder to change this variable. Okay, look at this picture. Okay, y is going to be x 1 minus x squared. X is between x is between 0 and 1. Okay, so rotation is about the x-axis. Okay, set up an integral for the surface area. Set. Okay. So how do you draw the graph, sketch the graph? Well, you draw the starting point, which is origin when x equals 0, y 0. You draw another point when x equals 1, y is also 0. But between 0 and 1, y is positive. Positive is the graph is about the x-axis. That's it, right? And then rotation is above the x-axis. Okay? So draw the picture, okay? I don't know the exact formula, but then you have x and y. You draw the radius, right? You write down what is r as y. Okay? Then you are going to use the x variable. So ds is 1 plus dy dx squared and dx. Okay. Y must be a function of x. Okay, so if you do then this area is going to be integral from 0 to 1, 2 pi. At the very beginning, you can simply write it like this. Okay, then you have to put details there because this is a integral with respect to x. So y variable depends on x, so it's going to be 1 minus this. Okay, then you differentiate y with respect to x. You will get, because y is going to be x times 1 plus x squared is x minus x cubed. When I differentiate, I get this. Okay, so that is going to be. I'm not able to change the variable to the y variable. Okay, I cannot change it to the y variable. Now, my question: if I look at this curve about the y-axis, how to do that? Yeah. Okay. For the same curve, I'm going to ask you to do that, okay? This is a curve. Y equals x, 1 minus x squared. Here's 1, here's 0. Rotation about the y-axis. Okay? So read this question carefully. It's not about x's. Don't just use the book formula in the book and without understanding. Set up the integral for the surface area. Okay? It's harder to draw the picture. It goes like that. Okay. A 3D graph, right? Okay. Something like that. Okay. So I want you to find the surface area of that picture. Okay. Right. How do you figure out the surface area? I think at this time you have to use x variable. You cannot use y variable. Okay, because you cannot solve for x in terms of y. So this is an arbitrary point, x and y. And the rotation is about this, right? So that would be the radius. Okay. Okay. Well, if we draw the picture correctly, then it's the rest of them is simple. I is going to be x, right? And ds should be equal to 1 plus dy over dx squared and dx. If you use x variable, x is between 0 and 1. That's it. Right? So the area is going to be integral from 0 to 1, 2 pi x 1 plus the derivative of y with respect to is already know that it's going to be 3x squared dx. Okay. Once you have this formula, you can enter. If you use the computer software, you can just enter the function and click. If you don't give you a very specific number, then you have to estimate, numerical estimation. So you can get estimate of the surface area. The computer can do that. What the computer does is use Riemann sums to approximate the integral. Okay, so accuracy depends on your setting. Okay. So you should clearly mark it clearly. What is the radius r? What is yeah? Then you decide which variable you're going to use. The original formula is only 2 pi r ds. Okay, this never be changed. But you can use x variable, you can use y variable for the integral. You decide that. Okay, and you have to figure out what is radius r. And clearly show, draw the picture, draw the r that helps you to avoid making mistakes. Okay, and you put the 1 point, you denote the coordinate at that point on the curve by x and y, and then R could be either X or could be Y.